I'm going to talk about climb performance theory today. This climb performance is going to be the next flight we will do after we do level flight performance. So while we get started on that, and then if we have time towards the end, we'll pick up some other things that we may have kind of skipped over. So we'll talk about climb performance theory, and then next time we will do the level flight performance flight, and see what we can do with that. All right. Well, a lot of things depend on the airplane's ability to climb, and we're going to be talking about two techniques, steady climbs and level acceleration. We're going to do steady climbs in the course. We'll probably demonstrate a level acceleration to you, but we won't ask you to collect and reduce that data. For years, the FAA did not require, in fact, the Cherokee 6 was not required to measure takeoff distance. Now, Piper did that. They measured takeoff distance for the Cherokee 6, and it's published in the handbook, but it was not required. The FAA, at that time, the FAA said, average pilot probably can't repeat takeoff distance. We'll talk about takeoff distance toward the end of the course, but the FAA said the average pilot probably can't repeat it. It's done by test pilots. It's generally done to show the airplane in the best light. And so instead the FAA put a requirement on climb. And that was that the rate of climb in feet per minute should be at least 10 times the stalling speed, which of course was in miles an hour at that time. Stalling speed, miles an hour, 10 times that in, forget about the units, 10 times that in feet per minute. Okay, so if you had an airplane that had a 60-mile-an-hour stall speed, then it had to climb at least 600 feet per minute in the takeoff configuration. That was the way they handled that particular requirement. That requirement generally set a maximum gross weight of the airplane, particularly for airplanes that had fixed gear or used as the Cherokee 6 does, 1 notch of flaps, 15 degrees of flap deflection, or takeoff. That climb requirement usually set what the gross weight was. So it was an important test, and what the FAA's thinking behind it was that if the airplane could climb that well, then it could probably get out of, take off and climb out of most airports by the average pilot. So that was the reason one of the reasons they didn't do takeoff tests. Well, years later along came the Environmental Protection Agency, who said, well, noise is a factor, and started out with just flyover noise. And then they said, well, no, we want to, where all the noise complaints are coming from are around airports. And so we need to determine, if the airplane can climb high enough, fast enough, so that the noise impact on the ground is not high. And as a result of that, the FAA changed those requirements so that you are required now to measure takeoff distance. And it all has to do with noise. It doesn't really have that much to do with performance, other than to determine what altitude you have to be over the microphone to measure the noise. And so anyway, that's a little history about takeoff distances and noise that I thought I'd throw out here at this time. two different techniques in climb testing, the steady climbs, and even today, that's about the only method the FAA will accept, even for transport airplanes, big airplanes, is the steady climb. The military, on the other hand, once particularly fighter airplanes, you know, I mean, when, for instance, when the F-15 came along, the F-15 could accelerate going straight up. How are you gonna get a steady climb with that? You're not, right? At least not at a reasonable altitude. Maybe when you get up 40, 50,000 feet, you can get in a steady climb. But that wouldn't work, so they had to come up with another method to determine what that would be, and the method is called a level acceleration. They just let the airplane accelerate the level, and then we'll see a little later that you can convert that to what a rate of climb at sea level would be, okay, at a given tick. But generally the steady climb method is used for lower performance airplanes and for all FAA climb testing, and the level acceleration is used for very high performance airplanes. Well, both of them come from the same equation, so we'll take a look at this, and we'll approach the theory in from two ways to end up at the same place. Those approaches are what we call the vector approach and the energy approach, and we'll start out with if we evaluate the airplane in a climb, and here's an airplane in a climb, and when we look at that equation, we see that, you know, the only reliable force, or only reliable, force vector we have on an airplane is the weight. Always points to the center of the earth. You know, the others, you're never sure where they're pointing. But the weight always points to the center of the earth, and if it's accelerating, it's a load factor in times the weight. Now, normally in a steady climb, for instance, we're going to be at a load factor of 1, right? So it's just going to be the weight. But if we look at that, we find that the lift is opposed by weight times the cosine of this flight path angle, okay? And of course, then we have this component that goes back here, which we add on to the drag of the airplane in order to get this. So if we write the equations for that sort of thing, we come up with something that looks like this bottom thing. In this case, we're assuming a small angle of attack. Thrust line acting along the direction of flight, which always does not always do that, but it's always pretty close, within a few degrees. And the airplane both climbing and, in this case, accelerating in the direction of flight, and then we can say that the lift is equal to the weight times the cosine of the flight path angle, and the thrust is equal to drag plus the weight times the sine of the flight path angle. And if we use Newton's second law, we can find, and by the way, you know, most all the aerodynamics, most all the physics we can get from Newton's second law. You know, Newton's second law, we can derive everything else if you're good at math. If you're not quite so good at math like me, you probably can't do that. But most of these things we can. And if we use Newton's second law, we say, well, the force in this thing is the thrust minus the drag minus the weight times psi gamma. That's equal to the mass times the acceleration. And the mass is weight over gravity, and the acceleration is the change in velocity with time, dv dt. And so if we transpose the weight times the sine and multiply through by the true airspeed, and divide through by the weight, we can rearrange this equation to look something like this, where we have the velocity over thrust minus the drag, divided by our times thrust minus drag, rather, divided by the weight, and that's equal to this velocity times the sine of the flight path angle plus V over G times dV dt. And if we draw a velocity diagram, we've got one here. If we draw a velocity diagram, here the airplane is along the velocity along the flight path. This is the flight path angle. This is the change in height with time on that, you know, and with trig we can solve several of these things. The rate of climb then becomes dH dt, or the change in height with time, and that's equal to the true airspeed times the sine of the flight path angle. And if we multiply previous equation through by the weight, the left-hand side becomes the thrust horsepower available minus the thrust horsepower required, you know, thrust minus drag, essentially, or the thrust horsepower in excess. And that's the excess power available to maneuver or to climb the airplane. So what you find if you work in this business for a while, you find if you add power to the airplane, it doesn't go a lot faster. Remember, because of that cube, when we looked last hour, we looked at that, you know, it's called the cube law. But the front side of that curve, the essentially parasite drag, is a function of velocity cubed. And so if you add, let's say you add 27 horsepower to your engine, your airspeed's only going to increase by the cube root of that, or 3 miles an hour, okay? However, for climb, that converts right into thrust horsepower in excess. So it's going to add you a lot of climb. So if you want better climb, you add power. If you want more speed, you better work on reducing the drag. Okay, because adding additional power isn't going to buy you as much in speed as it is in climb. And a lot of, you know, for years, prior to the gas crunch, the industry generally, you know, just put bigger engines. Bigger and bigger engines. Well, it helped with climb. It helped with the useful load because you could carry a bigger load because you had more thrust horsepower in excess. It didn't go much faster. And you burned a lot more gas when you did, due to the increase in the power. So we say the thrust horsepower in excess, that's the top equation there, is equal to the weight times the rate of climb, dH dt, plus W over G, the acceleration, the mass, times the acceleration times the true airspeed. That's the thrust horsepower in excess equation. And from that comes both of the methods that we're going to talk about. For instance, if we do a level acceleration, what is dH dt? Zero, right? Big zero. So that first term goes away. And we're left with the mass, W over G, times dV dt, which is acceleration times the true airspeed. However, if we say, okay, we're going to do a steady climb, or we're going to change dV dt to zero. Now we know that isn't exactly true. Why? Because as we're climbing, the true airspeed increases slightly. Okay, a little bit of change in true airspeed. But if we hold close enough, we can essentially say, you know, particularly at low performance, we can ignore that little change in true airspeed, and we can say dV dt is zero, and then we're left with the rate of climb equation. So we can kind of transfer that back and forth, which is what I've done, I think, on both of those slides. All right? And so from this one comes the level acceleration method. From this one comes steady climb method. Well, so we can say that really this combination of curves here, this one we talked about before lunch, that curve, okay? Well, here, if we got brake horsepower available with speed, that is pretty constant. And we put in the propeller efficiency, then we have the thrust horsepower available. This difference between these two curves is the thrust horsepower in excess. And so where this difference is the greatest is going to be what speed? The speed for best rate of climb. Right, that makes sense? Where those two are the farthest apart, we're plotting this versus airspeed here. Where this is the greatest, as I spread my, it's right along in here someplace, because after this it starts to come down. So it's right along in here on these curves that I've drawn. Well, that corresponding speed is the speed for best rate of climb. Actually, you can say that combined within these two curves is the total performance of the airplane. Okay, because you have this bottom one covers level flight, this top one covers, encloses the thrust horsepower in excess. So depending on what this distance is, this place would also be, this widest place, this best rate of climb, would also be the place where you would get the maximum acceleration. Right? And any place other than that, speed-wise, it would be something less. Well, unfortunately, thrust horsepower required and thrust horsepower available are difficult to obtain because both of them contain propeller efficiency. If we go back to this curve, both of these have propeller efficiency in them. Now, I've drawn a propeller efficiency here with this one, but so does this one contain propeller efficiency. So because it was even measured in steady flight, but it still contains propeller efficiency. But thrust horsepower in excess, the difference between those two, we can obtain that by from climb or acceleration, and it's going to become zero at the stalling speed power on, and that's on the left-hand side of that curve. Okay, so here's the stalling speed power on right here. Okay, out here where the two cross, maximum level flight speed. And at those 2 points, rate of climb 0. Or acceleration is 0.
So the F-15 crosses out there somewhere. I need to visit it all.
There's a place out here called the Mach. Okay, and the F-15 crosses out here someplace. Okay. Now, what happens once you get beyond the mock, you know, this curve goes up and it goes way up when you get to the mock, okay? And, well, let me draw it. Even though it's hard to erase. Let's say this is Mach 1. You know, this curve is going to look something like this, subsonic. And it's going to go up here and it's going to do this thing, and then it's going to way out here about, it comes down and kind of flattens out. And of course, let's say this is our thrust available. Well, you can see out here, right here at Mach 1, we don't have much either acceleration or rate of climb. In early jet airplanes, what they did, actually this top curve would be something like this.
Go to the dive and punch through it.
They had to get out to here and dive, go supersonic, and then once they were supersonic, they could maneuver and perform. Even today, still the quickest way to get to a given energy state is to do that technique. You climb at a given time and then you dive to get supersonic, and then you can go to another energy state. We'll try to talk about that before we get
With
through the
propeller
course.
driven airplanes in World War II tried to do that, and they had stability and control problems.
Yeah, and of course, you know, propeller-driven airplanes, you get close to Mach, thrust really goes to hell, okay? It just goes to, you know, little or nothing. And the noise goes completely out of sight. If you hear an airplane take off out here, and he's making a lot of noise, it's generally propeller noise, okay? It's a propeller-driven airplane. It's propeller noise rather than engine noise. And that propeller out close to the tip is getting very near, if not at, sonic speed. So, like I say, what you can learn off of these two curves if you have them. Well, we can plot this another way. We can take that difference, you know, we can take this difference between these two curves, and we can just plot the difference. And that's what we've done on this one. And we can convert this from thrust horsepower in excess to rate of climb. And that's what I'm saying here. And you've probably seen curves that look like this, okay? Down here, that's power on stall speed, okay? Out here, max level flight speed. If you're developing these curves, you know, one of the things we did with propeller-driven airplanes is we'd go out and say this is low altitude. We'd go out at low altitude and we'd fly opposite heading climbs here and here and here and here and here and here, and then maybe do a max level flight to get that point, power on stall speed to get this point, and then be able to curve through there. Now, my previous job, I had a Cessna 310, which was actually an Air Force U-3A. And somehow, we'd come across the flight test, Edwards flight test report for that airplane. And they had developed these curves. However, it looked like somebody had the data points looked like somebody had got back with a shotgun and backed up to that wall and fired at the graph papers, okay? And there were all these data points, and then they drew this curve through, smooth curve through all these data points. I used to use that as an example for my students, that here, you know, this is what the real good guys out at Edwards got for you on this kind of an airplane. So don't expect your data to look a lot better. But anyway, a couple of things to notice. If you draw a line tangent to that curve, horizontal line tangent to it, again, that's the best rate of climb speed right at the top, okay? And if you do one at a higher altitude, and we used to have to do 3 altitudes of this, ever 5 knots. That took forever, flight test wise. It's really time consuming to find best rate of climb speed if you do it this way, okay? Really time consuming. And you get those two, and then you can draw up a curve. But the other thing is, you draw from the origin, tangent to the curve. That is the best angle of climb speed. You've probably seen that. That's the speed that you want to fly at if off the end of the runway is a big tall tower and you want to clear it. You don't fly at best rate climb speed because you'll probably clip the top of the tower off, okay? Because your best rate